So here we're going to look at bond enthalpies. It's a way you can find delta H for the reaction. We'll write that maybe over here just so you... That's what we're going to be finding, delta H. How do we find delta H for a reaction using bond enthalpies? So I will first off say using bond enthalpies to find delta H is kind of convoluted, and it's not actually the more accurate way to do it. We'll put up a video using heats of formation, which going forward you'll probably use a lot more than bond enthalpies. So what a bond enthalpy is, what we're finding here is, if you were to picture, for example, this CH4 molecule right here, say we had that, the energy to actually rip off every one of those hydrogens. So when you're doing bond enthalpies, it's sometimes helpful, in fact I think it's always helpful, to draw out what you're looking at. So this is CH4. There's 4 hydrogen attached to a carbon there. Oxygen, this is elemental. So we got that guy going on, 2 of those. CO2, carbon wants 4 bonds. You can actually probably draw it. Let's change colors here. And plus there, plus here. And H2O. Oops. Okay. So while we're doing this here, we're just kind of looking at what is the energy associated with every one of these bonds. So this hydrogen bond, that hydrogen bond, this one, and we're calculating all of those energies. And we're going to calculate this, and we're going to do reactants minus products for this. So you've probably seen it, it's just a sigma sign, means you're adding up all of your reactants first. Reactants minus the summation of all of your products. And you'll actually look these values up, say in a table of bond enthalpies. And every textbook kind of varies a little bit as to what they say they are. That's okay. It doesn't vary by a lot. So if you look up a CH bond enthalpy, you'll probably get something like 411 kilojoules per mole. So 411 kilojoules per mole. That's to tear off one of these. If you just picture you walked up and ripped that hydrogen off of there, that's how much energy it's going to take you. So what you have to take into account, what you have to think about, you have 4 hydrogens on this carbon right here. So you can call that 4 moles of hydrogen there. With that, because this is a summation, we're going to add oxygen. So if you were to look that up, if we were to rip this guy apart right here, it's going to be about 494 kilojoules per mole. 494 kilojoules per mole. But go back up to our balanced equation. That's something you have to remember. This up here, this chemical equation has to be balanced. And we have a stoichiometric coefficient of 2. This 4 was in reference to the 4 on here. If I had if I had a 2 out here, if this is how this was supposed to look, it would be these 4 multiplied by that 2. This would end up being 8. That's not the case. And that's why this gets a little confusing. Right here, I'm only breaking one set of bonds. It is a double bond, but it's only one time. I have to break both of those to separate the oxygens. So that's one, kind of tearing apart happening there. And we have 2 moles of that happening in our stoichiometric, for our stoichiometric coefficient. So let's move on here. This is going to be, those are our reactants, minus, and I like to put a big bracket here, because if you just plug everything across in your calculator, you'll probably get an incorrect answer. This is going to be CO2, and if we were to look that up, we probably get something like 799 kilojoules per mole. And oftentimes textbooks will have a separate, you might find an asterisk, a separate notation for the actual value of the CO2 being ripped apart as compared to just a normal CO bond being torn apart. A carbonyl could be vastly different than just this molecule of CO2 being torn apart. So you'll see we have 2 of those here. And that means this is going to have 2 moles out front here. And I should probably be consistent and make sure this says moles. That's for that 2. Forgot to write it in there. Make that look a little better. Two moles. And this is going to be plus, and then H2O. So each OH bond being torn apart, that's ripping this hydrogen off and that hydrogen off. 459 kilojoules per mole. Now, we have to look up here and say we have two moles of this, and our stoichiometric coefficient is 2. We also have 2 bonds per molecule. So you can think about it in a way I like to think about it is how many total bonds are there all together. I have 2 here, but I have 2 moles of this, so you could almost say there's 2 water molecules. So there is. It's going to be 2 times 2 is 4. 4 moles. I wrote moles here so that that'll cancel on all of them, leaving us with just kilojoules. Close our bracket over here. The reason I put these brackets here is if you type this into your calculator, 4 times 411 plus 2 times 494 minus 2 times 799, it's not going to add all of these together and then subtract it from what these are. It's going to give you an incorrect answer. So either put it into your calculator with the correct brackets or figure out what the entire sum of this is and subtract that from this entire sum of this. Now, I didn't do this calculation recently. I'm just looking through old notes. And it looks like this was equal to, actually, looks like it's probably rounded, about equal to 812 kilojoules. Wondering if that was supposed to be negative. You guys can do that and tell me. So next what we'll look at is heats of formation, and that'll be in another video, and that's going to be a lot more relevant than this. Heats of formation you'll probably use a lot going forward, especially if you're doing more chemistry, if you get into physical chemistry. It's a little more accurate, it's a little more useful, and it's actually a lot easier than this too. So bond enthalpy is more difficult than heats of formation. There's a lot to take into account up here with your stoichiometric coefficients and how many bonds you have, where heats of formation will involve this particular specific molecule and give you a value for that. This down here will change though. So right now we're doing reactants minus products. That will switch going forward. But for bond enthalpies, reactants minus products. If you liked, then go ahead and like the video and subscribe and share. If you're watching this, I'm trying to add this on to the original video. Probably said something like we had delta H being equal to about 812 kilojoules. So that's what I had written down in my notes. After doing the video, I went back and looked at it. Maybe my professor was wrong. I don't know. I could have written it down wrong. But it looks like it should be. This is not right. No. Looks like we should have. Let's even change colors here. Delta H is about negative 802 kilojoules. That kind of makes more sense because if you look at the heats of formation, you'll see that it's about that. It's negative. It's a negative enthalpy. And so this should be more correct for it. Hopefully this will add okay to the original video. We'll see how that goes. If not, I'll figure something else out. But yeah, don't think that was right. So that should be a little better.